si può togliere con...
Sì.
Ok.
Ok, c'è questa. Si riesce a spostare un po' meglio. Vabbè, ok. So, okay, it's with great pleasure that I'm going to introduce the speaker of today. She's Lara Pantoni. Lara did her master thesis here in Bologna, working with me, Margherita Taglia and Andrea Cimatti. And during her master thesis, she analyzed the dusty galaxy at, let's say, high redshift around 2. And she was focused on the estimation of the dust masses. Then she got a PhD in Sissa, where she worked with Andrea Lappi. So she moved from where she did both from where she did the galaxy evolution, both from a theoretical point of view and an observational point of view. And then now she has started last November a postdoc in Paris, Saclay. And now she's still studying the dust, but in the local universe. So now she's more focused on studying the physics of the dust, not just, let's say, just to estimate the masses. So I give the floor to Lara.
Thank you for the introduction. Indeed, today I will present a study that came out from my PhD work at Sissa and is based on these 2 papers that I report here. Before going into the details of these 11 dusty star-forming galaxies observed at the cosmic noon, I would like to introduce, how can I go on the slides here? Okay.
Just
Sorry,
using a better microphone, hopefully.
Okay. Okay. Okay, I would like to.
Doesn't work. It's too hot.
Yeah, sorry, it's a bit small. Okay. So what are the star-forming galaxies at high redshift? They are an abundant population that was discovered almost 10 years ago from the first sub-millimeter survey with the SCUBA, and later on with Herschel, we were able to observe more than 1 million of high redshift dusty galaxies that are luminous in the far infrared restraint. These galaxies, so here I show a typical spectral energy distribution of dusty galaxy at high redshift, actually at increasing redshift. And you can see that these galaxies are very convenient to be observed in the sub-millimeter wavelength range, thanks to the negative K correction that shifts the peak of the LCD into the observed band. They are very attenuated in the optical UV band, and most of their luminosity comes from the infrared indeed. They are massive. Typical stellar masses are higher than 10 to the 10 solar masses, and they feature star-formation rates larger than hundreds of solar masses per year. For this reason, these galaxies are very important for constraining, for studying massive galaxy evolution. They are mostly observed at redshift larger than 1, in particular at redshift in the range 2-4, where the cosmic star formation rate density peak. And for this reason, they are thought to play a major role in the cosmic stellar mass assembly. Moreover, the cosmic star formation history resemble very well the black hole accretion history, which peaks at the same redshift. For this reason, studying the star-forming galaxies at the cosmic noon is very important to shed light onto galaxy black hole coevolution. These dusty galaxies at high redshift are thought to be the progenitors of local massive quiescent galaxies, and there are on the market three emerging theoretical scenarios. The first one, that is known as merger-driven scenario, assume that merging event between gas-rich spiral galaxies at high redshift are the main trigger of the star formation inside the galaxies and the accretion of matter onto the central black hole, which eventually quenches the star formation and drives the morphological transition to massive quiescence in the local universe. A second alternative scenario is the one which claims that steady stream of cold gas from the cosmic web are responsible for the ongoing star formation activity in the galaxy and can eventually also be responsible for the transition to a spheroidal galaxy. The third scenario is the so-called in situ galaxy black hole coevolution, which describes the star formation activity in the galaxy and the central black hole accretion as in situ time coordinated processes, which regulates the subsequent evolution of the galaxy and also the quenching of the star formation activity due to AGN feedback. For the interpretation of the observational results in this talk, I will refer to the third scenario in order to provide self-consistent theoretical interpretation. To address the problem of massive galaxy evolution, usually we can usually use two different approaches. Analyzing statistical sample of galaxies, which can constrain a specific property of the galaxy, for example, the stellar mass, the attenuation in the band, or the dust mass. But in this case, we decided to focus on a small sample of galaxies in order to gain deep insights into the astrophysical processes which have a role on the evolution of the galaxy. This allowed us to have a complete coverage of galaxy multi-wavelength emission, to have spectral line emission, in particular CO, and to have spectral redshift for these galaxies in order to not introduce too many uncertainties in the analysis. Okay, the sample has been selected in the sub-millimeter regime using ALMA, Aztec, and Laboca map, and then we performed in the God South field, and then we performed a sky match in order to have to cover the emission of the galaxies from the X-ray to the radio band. To this aim, we required at least one spectroscopic determination of the redshift, and indeed here you can see the redshift distribution of the galaxies, which peaks at redshift 2, and also at least 3 detections in the optical, 6 in the near mid-infrared, 2 in the far-infrared, and at least 1 in the radio X-rays. In the bottom right corner, you can see the typical sampling of the galaxies in our sample. We end in such a way with 11 dusty star-forming galaxies that for which we model the spectral energy distribution using SIGAL, which is a Python code based on the energy balance principle between the light absorbed by dust emitted by in the UV optical by the stellar component, and then re-emitted thermally in the far infrared. These are the modules and the priors we used for the free parameters. Then if you want, we can talk about it a little bit deeper. And here you can see the spectral, the SED and the best fit for each galaxy. We didn't include in the fit a priori the radio point, since it was not possible to constrain the far infrared radio flux ratio with just one point, but we compared the radio emission that is in yellow with the typical emission expected from star formation only. And we see that for all galaxies, they are consistent. So the radio emission from each galaxy comes from star formation only. While from the X-ray emission, we were able to understand if the galaxy hosts an X-ray AGN. For 2/11 galaxies, the X-ray emission is actually dominated by the central AGN, while for the others, the luminosity in the X-rays is actually greater than 10 to the 42 ergs per second, indicating that we could have an AGN, but its emission doesn't overwhelm the one coming from the star formation activity of the galaxy. From the SED fitting, we can say that these galaxies are almost on the main sequence. Here I show the median values for stellar masses, star formation rate. They are experiencing an intense burst of star formation that is quite short. The duration is less than 1 gigayear. The dust content is very high, and it has been formed in less than 100 of megayear. The depletion time scale is of the order of a few hundreds of megayear, and this this is important to understand the actual evolutionary phase of that are experiencing this galaxy. However, since okay, we'll skip this. Okay, since many of the majority of the processes leading the evolution of the galaxies are actually occurring within the galaxy. So in a region that is smaller than 10th of kiloparsec, to study these processes into the details, we need the sub-second resolution. And for this reason, we look for some specially resolved images, multi-wavelength images of these galaxies. We had already the HST images that were resolved, so we were able to estimate the size of the galaxy. But in the ALM archive, we look for observation with angular resolution smaller than 1 arc second, and we found 6 out of 11 galaxies that are actually spatially resolved, so we were able to estimate the size. And it is very important because the in situ scenario is able to predict the size of the optical counterpart, the size of where we have the mildly obscured star formation occurring, and the size of the far infrared, the dust obscured emission, where the most intense burst of star formation is occurring. In such a way, we were able to constrain we had an additional information for constraining the stage, the phase of these dusty galaxies. Moreover, we were able also to trace the cold dust phase in these galaxies by the detection of 5 CO lines for 4 galaxies that actually have been found in the ALM archive. I would like to give two specific examples in order to show you how all these piece of analysis can give information on the evolution of the galaxies. In the case of UDF1, we had, thanks to the SED15, the stellar mass, the star formation rate, the luminosity in the X-ray and the infrared. This allowed us to put the galaxy onto the main sequence. And actually, we see that the galaxy is just above the main sequence of star-forming galaxy. The X-ray luminosity exceeds the host emission, so actually we have there an AGN emitting in the X-ray, and following the prescription from the in situ scenario, this is exactly what we expect for a galaxy onto the main sequence that is thought to evolve in this way, forming stars almost constantly, and then at this point we have the AGN power overwhelming the one of the galaxy, quenching the star formation, and then the galaxy becomes an acquiescent massive one. So here we are in the phase in which the AGN is still accreting material, but it is becoming luminous in the X-rays. Then, by looking at the ALMA in the HST emission, we actually see, as predicted by the in situ scenario, that the ALMA radius is quite compact with respect to the optical radius, and indeed it is what is predicted by the in situ scenario. Here on the right you can see the size mass relation, where the blue line stands for the stability radius to gas fragmentation, where we have the mildly obscured star formation activity of the galaxy. The gas, you have to imagine the gas going, migrating towards the central region of the galaxy, and in the very center, the dust obscured star formation ignites, where this area is defined by the rotational radius, where the rotational support and the gravitational pull balance, and then further migration toward the center are possible only with gravitational torques, for example. As you can see, the HST size is exactly in where so should be between this blue radius and the red one, while we expect the far infrared to be lower, to be smaller than the rotational radius. So what we are observing here is a galaxy still forming stars. The gas moving towards the center of the galaxy is also fueling the accretion of matter onto the central black holes, but we are still in the phase in which gas is going towards the center, and we have star formation ignited both at larger radii and in the very inner part of the galaxy. What we can learn then from the CO emission, for UDF1, we detected, actually we found on the ALMA archive a CO32 line that show a single peak, and it means that we are observing based on rotating disk of molecular gas, and it is also confirmed by the momentum to map that is picked at the center, and from the velocity map, that for which we can see that the velocity range covered by the CO emission is actually spans actually the range of 60 kilometers per second, resembling the chaotic motion of the cold gas phase. We couldn't constrain the size of CO. We just give an upper limit that is in between the size, the far-infrared size and the optical size. We estimated we measured the molecular gas mass and the depletion time scale that in this case is of 100 of mega-year, confirming actually what the scenario I depicted before. Here I have another interesting case that is the one of ALES 67.1. For this galaxy, we had the 2 detection in the radio, so we were able to perform the fit, including the radio emission, and deriving some value for the far-infrared radio flux ratio that are actually consistent with what has been found for statistical sample of galaxy. Again, with the outcome from SED fitting, we placed the galaxy onto the main sequence, and it is actually a main sequence galaxy. And we can see here that the X-ray luminosity is consistent with the star formation, but it is larger than 10 to the 42 ergs per second. And for this, for luminosity higher of this value, we actually we can have a contamination from the central AGN emitting in the X-ray. Again, using the spatially resolved images, we were able to constrain the prediction from in situ scenario, and you can see again that the results are pretty well matched. This is a quite a different case because you can see in the optical map that we have different clumps. That could be star-forming clumps, or someone claimed that they could be companion galaxies eventually interacting in a merging. But we actually favored the first scenario since the scale is not that large, is within 10 kiloparsecs. Moreover, a confirmation is also draw from the CO spectral line emission. Indeed, is it true that the momenta are a little bit disturbed, but not that much to justify a merging event? We could also think about an AGN-driven molecular outflow, but I'm not sure. Actually, we can see here in the PV plot a peak at 800 kilometers per second, but it could be just noise. So this is not sure, and we definitely need imaging at higher spatial and spectral resolution to definitely disentangle these different scenarios. So I will finish with my conclusions. These 11 dusty star-forming galaxies are main sequence objects. They are experiencing an intense, short, and dusty burst of star formation. They are rich of dust and cold gas. Most of them are hosting an AGN emitting in the X-rays. Some of them, for 2 of them, the X-ray emission from the AGN overwhelmed the one coming from the star formation activity of the galaxy. The AGN are if we have actually AGN, they should be radio silent or quiet, and this is also predicted from the in situ scenario. They are compact, both in the optical and in the far infrared and radio band. but we saw for all the galaxies that the HSTA emission is extends over a larger radius than the far infrared one. By looking at the environment, we saw both isolated or disturbed clump morphology in the H-band. They are then caught in the compaction phase when we have the gas migrating towards the center and the mildly obscured star formation at larger radii, the dust obscured star formation in the inner part, and the accretion of matter onto the central black hole. And we expect them to be quenched by the AGN feedback in hundreds of megayears. As I said before, we need better data to better constrain the possible scenario. I thank you for the attention, and I'm open to questions.
Thanks. Let me see if there are questions also from the remote audience. Okay. Meanwhile, are there questions for our speaker? From the room. Yeah.
Well, very nice. I have several questions. Maybe we can talk about after.
Sure.
I would only ask if here one that is more on the interpretation. I very much appreciate the effort to put all these observations in evolutionary sequence. This is always extremely difficult, and one example I can think of is if you take, for instance, Andromeda, which is definitely not in the evolutionary stage think of, and you see the extended disk, you would see the rest UV is much more extended than the ring where the dust emission comes from, especially if you cherry pick the part with the higher dust temperature, which is probably what you see you pick up and down. So in that case, that galaxy would kind of fulfill the fact that you have smaller radius for the dust, a bigger radius for the UV, and yet it doesn't follow the evolutionary picture you present. If you could clarify.
Yes, so I think that the first thing is that we should be how to say, we know that what's happening at high redshift is actually different for the local galaxies, and indeed this model works if you applied it at high redshift. So on galaxies that are massive and forming stars at redshift greater than 1. Indeed, it's true what you said, but I would not interpret the evolution of Andromeda with this model. So I think that the first step is to ask, am I at high redshift? So for describing these objects, this could work. At slower redshift, I have to take into account other processes, because the evolution of local disk spiral galaxies is almost secular. So you have processes that are not happening in this case because the evolution of these galaxies is too fast. So you have to take other processes into account, and the model would be different.
Yeah, no.
But I was
wondering if,
yeah,
for instance, ALS 67 could be like Andromeda, could be more affected by a more secular process.
Well, in this case, you also okay, I see. Well, the thing is, find a way to constrain the fact that the galaxy is experiencing secular processes by using observation. So I think that if you can demonstrate it, then we can discuss. But in this case, since due to the star formation rate, the dust content, also the morphology, you have this very clumpy morphology in the HST map. I won't expect a secular evolution because everything is happening very fast. The star formation is very high, and then you have a very short depletion time scale. So I would say no, but you know, in science, if someone can use another model to explain it, we can talk about it.
So your plots of the size mass,
Yes.
you also have a line that is indicating this range for stability. So I was
Yes.
curious about more details about how this is computed, or in case you could be from somewhere where.
Yes, this is computed in Lapie et al. 2018, where there is a very detailed description of the in situ galaxy black hole coevolution, in particular regarding the size mass evolution. And this stability radius, you mean the rotational one, I think, but both, every radii there are computing by taking into account the typical time scale of migration and all the processes happening to the gas phase. So yes, I refer to that paper.
Yes, also I cannot do the details.
Yeah.
Yes,
Yes.
the reference is.
Yes.
Let me see if the remote audience has. I think it's really too hot even for the Mac, which is now stalling. Perfect. It doesn't seem so incredibly hot, but all in this room, all devices are going banana. But anyway, okay. I don't see any question from the remote audience. Okay, so I think we can just thank the speaker again. And we still have a talk next week on Tuesday again. Bye everyone.
Non c'è problema. Tanto siamo riusciti, quello è l'importante.
No, tipo lo schermo.